Is my screen visible? Yes, no. I'm not able to hear you. Am I audible in the first place? Hello.
Yeah, visible.
You're
Oh,
audible, sir.
screen is also visible?
Yes,
Yes,
sir.
sir.
Okay, okay. ठीक. So let me start now. So today's topic is on linear regression, and so we will first start with defining what machine learning is, what kind of problems does machine learning solves, and then look into the first model that's called linear regression. So before we start, let's look into what machine learning is. So machine learning is not a recent topic. It's studied from 1950s and slightly even more though. To be frank, the first paper that was published in machine learning was in 1930. So it's that old. But the proper definition came from Arthur Samuel, and he just says the machine learning is a field of study that gives computer the ability to learn without being explicitly programmed. So when I say explicitly programmed, it is that you write a if-else statement. Like if you do this mathematical equation and return the result. This is what I meant explicitly programmed. You don't explicitly say what you have to do at certain instances, but you give the computer the ability to learn and adapt through data. That's how he defined the machine learning, and more or less, this definition still remains very intact. You want computers to give the ability to learn, and this ability to learn is the method that we call the machine learning. So we still want to want to give the computer the ability to learn through data set. That you have some data and you want the machine to learn through this data set for some task that is user defined task, and we will evaluate that performance on some metric, like whether the metric is accuracy, that how accurately your computer is able to predict certain things. So for example, it has to predict whether there will be a cyclone tomorrow or not, and if your computer can predict such a thing and how accurately it can predict it, that's called the accuracy. Okay, so this is what machine learning is as defined by Arthur Samuel. Now, the purpose of machine learning could be many things. So, so my is a pointer also visible? No. Yes. Mm, my am I audible in the? I get confused. Is my pointer visible? Sorry.
Yes, sir.
Okay. Okay. So, so in machine learning, what we have is we have a set of data set, and it goes through some machine learning model. And the task could be to identify some pattern or relationship between the data set. So, for example, you want to identify a pattern that are all these data that you are seeing are of, say, category, are all the news articles that you are reading is of politics news, or all these data that you are reading is of sports news. What category of these data are? So you want to find a pattern in it, or some form of relationship, whether the data point one has any relationship with data point two in your data set. So you want to identify a pattern in it, or a relationship in it, or you want to find some insight that is insight into the unknown data set. So for example, these are the data set that you're feeding into your model, and the unknown insight could be, say, if you look at the GDP numbers of the country, say you have the GDP data for all the years of your all the countries in the world, and then we want to find the insight that is the poverty in the world decreasing or increasing? What is the ratio? At what percentage are we? The poverty is declining in the world, or if it is staying the same? You want to find such insight from this data set that is not visible directly from individual data point. or you want to make informed decision. Say, for example, given the GDP numbers of our country, what decision would be a better decision to improve our GDP number or improve our education metric given these data set. So there can be multiple questions that you want to solve using machine learning. Either you want to identify a pattern in a relationship, you want to gain a new insight from this data set, or you want to make a decision with this data set. It depends upon the user or the user of the application of this machine learning model. What you are using this machine learning for, they will decide what this pattern should be. So as a role for you is to design a machine learning model such that these questions, either of these questions that the user want or the person who needs can answer it. So your goal is to design this machine learning model. Okay, so there are multiple types. There are specifically, broadly specifying, there are three categories of machine learning, which we call it unsupervised learning, supervised learning, and reinforcement learning. So these are the three broad categories, and among these broad categories, there are multiple subclassifications again. So say, let's look into the supervised learning part first. Supervised learning, there are two categories there. Here, the one category is classification and the other is regression. So in supervised learning, in most supervised learning algorithm, the standard supervised learning algorithm, you have a data point, and for the corresponding data point, you also have some some label corresponding to it. So we see there is a classification category where the classification category is simply to predict whether uh, predict a class for this data point. So let's take an example of this classification. So there are images of animals, and given an image of an animal, your classification model will say whether if it is a dog or not. So dog one, not a dog zero. So based on this classification model just simply predicts one or zero given a image animal. In regression model, so given an input x, you want to predict a continuous value. So for example, given the location and time, you want to predict the temperature at that particular point period. Given the location and time, you want to predict the temperature of that place. So this temperature can be a number between uh, can actually go for any numbers, but say for realistic case, let's assume for minus 5 degrees Celsius till 45 or 50 degrees Celsius. So it can predict any number in between minus 5 to 50. So it can be 43.2, it can be 45.5. It can predict any number in this continuous range. So classification is a prediction of a label, a category, and regression is a prediction of a continuous number. So you have the supervised learning algorithm. Unsupervised learning algorithm is slightly different. Here, your goal is to understand. In supervised learning, your goal is to predict. In unsupervised learning algorithm, your goal is not to predict because there is no such label. Your goal is to identify the relationship between the data set. So, for example, you have a very large data set, like very large number of data set. So, you want one thing that you can do is you want to reduce the size of the dimensionality. Say, for example, a person X can have many features. Say, for example, you can have your name, address, age, education background, your date of birth, your what kind of color of clothes you are wearing today. Also, so many. So you can make hundreds of features from you, but not all features are necessary for, say, categorizing what is your mm, age. Only your birth information might be sufficient to give away what would be your age. All these categories that I added there, that the color of your clothes, which place you live, what school you went to, all these information are unnecessary to decide what is your age. Your date of birth feature itself is sufficient to give the answer for about your age. This is a very simple example, but consider there are very large number of features for a single data point. You want to reduce that so many features into a few set of features. That's what dimensionality reduction is. So you want this dimensionality reduction is very meaningful in compressing the data set. So you have a very large data set if you have so many data points, but if you can compress into very few data points and still do not lose accuracy, that's what you want to do, dimensionality reduction. And clustering. Clustering algorithm is to find relationship between the data points. Say you want to cluster all the politics based news article. This is one cluster. You want to cluster all the sports based news article. That would be another cluster. See, those are clustering algorithms. So in our machine learning algorithm, in this course, we will be looking into both regression classification, dimensionality reduction, clustering. So these four will be covering in our course. And the last part is reinforcement learning. This we will not be covering. This is about learning through trial and error. So the game, remember how we learned to bicycle? We first tried bicycle and we tried to paddle and we fell and we received a signal that, oh, this is not how we should be doing it. We should actually paddle it more properly. We should handle the we should hold our handles more steadily, properly balancing it. We fell again and again, and then eventually we ended up learning how to ride our bicycle. The way we learned is through trial and error. Reinforcement learning is also a set of algorithms that learns through trial and error. So this part, we will not be covering this part itself is a very long, broad field. So we will not be covering in our lectures reinforcement learning, but we will be covering supervised learning and unsupervised learning. So today's topic is on regression, but before we actually go to regression, let's understand supervised learning in more better detail with examples now. So in supervised learning, you have some data. It can be a continuous data when you have to solve regression. Remember the example of predicting temperature? That's what continuous data means, that it is a continuous value between some range. And if you want to do a prediction in that continuous value, that's regression. Categorical simply means that you have fixed set of categories, say one, two, you have five set of categories and you want to predict among these five sets. So among a very few sets of categories, that's what prediction if you have to do in this set, that's called classification. So continuous, it's a regression, and for a few set of categories you want to predict, that's classification. So the prediction problem is a supervised learning problem. Unsupervised learning is the kind of things that you want to do. So if you have a continuous data set, so you probably want to do a dimensionality reduction, and for categorical things, you probably want to do a clustering problem type. So this is not unsupervised learning. This is not a hard and fast rule, but in general, you can take it for this way in unsupervised learning case. Okay. So unsupervised learning, you don't make a prediction. You actually do either some finding a relationship between the data, or you want to reduce the dimensionality of the data set. You want to reduce the size of the data. So unsupervised learning helps you find relationship. Supervised learning helps you in prediction. So let's look into this type of problem. So you have some feature. This is X. There is this. These are features. So this is some item which has feature 1 is 12.7 and feature 2 is 136. And this feature, this item with X1 and X2 corresponds to a label of 0. Okay, so there are only two labels, 0 and 1. This is for another item has feature 45 and the same item had a feature X2 as 87, and this has a label of 1. So given this data set, this first three row data set and its corresponding label 0, 1 and 0, your goal is to train a prediction model such that given this new data point 56.9 and 99.4, you want to predict what is the corresponding label. Is it either 0 or is it 1? What kind of problem is this? Is it a regression problem or is it a classification problem? Anyone? What kind of problem is this? Is it a classification problem or a regression problem? Hello? Say something. Matlab, is it? What do you think? Is it a classification problem or a regression problem?
Classification.
How? Correct. It's a classification problem because your goal is to predict among these two set. Either it can be
Label.
zero. Yeah, it can be either be zero or it can be one. So this problem is also a classification problem. Here, this new data point is given to you 56.9 and 99.4. So what is the label corresponding to it? It's either 0 or 1. Hence, it's a classification problem. So this is kind of problems are classification problem where you have to predict within a given set of labels. Here, 0 and 1. Now let's look into this type of problem. Here you have some information. You have a person's ID number 10, education is some level 16. I don't know how they are measured, and whether it has gone through a professional training or not. So one means professional went through a professional training, and it has not gone through a professional training. And what is this person's hourly rate? How much he is going to charge? So the goal is that these are the information about a person 10, 16, 1, for this person's 2, for ID number 45, education 50, he doesn't have a professional training 0, and his hourly rate is 65. Now, these are the blue colored mark. So, blue colored marked are the one that you want to predict, and this gray, the light green that you are saying, assume that these informations are not available for you. For the timing, just assume 65, 130, and 110 are not available to you. What kind of problem is this? That you have to predict the hourly rate of a given person. Say this given person number 2, 45, 15, and 0, and you need to predict the hourly rate. What kind of problem is this? Is this a classification problem or a regression problem?
This is regression, maybe because the data is dependent on each other.
Data is dependent, I agree, but why is it a regression problem?
And then we are deriving something by analyzing the relationship between them.
I will say that you are partially correct, but it is not the correct answer though. But it is a regression problem because you have to predict among the continuous sequence. So the hourly rate can from be 0 till you can see it goes to 130. Maybe 200 is the maximum number. So it can predict between 0 to 200, and the rate can be 99.5, 99.7. So there are infinite number of values, right?
Okay.
So since it's a continuous value prediction, that's called regression problem. Any place that you see, there is not a fixed set of a finite set, the prediction is made in an infinite set. It's mostly a regression problem. Okay.
Yeah, noted, sir. Thanks.
So let's redo this thing again. This is a classification problem because the labels is on a fixed set. Here the set size is 2. You have a fixed set size of 2. Here, the hourly rate that you have to predict is an infinite set. From 0 to say 200 is the size. So it can predict any number between 0 to 200. It can be 99.3, 27.6, 0, 200, 99, 199.7, 187.6. Any number between them it can predict, and there are infinite such numbers. So this is a regression problem, even though the data are definitely dependent. Now, this is how the problem will look like. Now, in general, you will have two set. First is a training set. So all the blue marked numbers that you are saying is a training set, and this gray thing that you are saying, the light green that you are seeing here, are the test set. So there is a reason we divide into a train set and a test set. Since we are training our model, we train set simply means that you will use these blue colored data points to train your machine learning model. And once the machine learning model has been trained, you will use these test set data points to find the prediction accuracy of these models. How accurate are these models on these test set that it has never seen in the training data points? If it can say that if the accuracy on the test set is say 100%, you can say that the model has trained really well. If the accuracy on the test set is say close to zero, then you can say that this model is completely useless. You cannot rely on this model, because in real world you want to use this model in real data set. When you don't have any other information, a new data point will come to this model and it should be able to predict with sufficient accuracy that what will be the correct answer for this data point. That's why we divide our data points into train and test set, such that we can test the model's accuracy or the prediction accuracy on the test set. So is this thing clear? Why are we dividing in our data into train set and test set? Uh, can someone say something? Is it should I repeat why should we divide train set and test set, or it's okay? Okay, so I will assume that it's okay then. Okay, so in machine learning, your problem becomes you first need to understand what your problem statement is, what data is available to you. Then, based on that data, you extract what all features you from the data set you will actually be using to construct your model. Then you identify whether it's a classification problem or a regression problem that you want to solve. Then you build your model. Once you build your model, you need to train your model and test the model on the test set that you have created. And then you try to find, once you have the model and you have trained your model, then you actually evaluate your model on the test data set. And if you see that the model has performed really poor on the test data set, you go back to your model selection, you decide on a different model, train it again on the test trained set, and then test on the test set. Once you have achieved a proper amount of accuracy, whatever accuracy you want, once you have reached that accuracy, and then you give that model to the user, whoever is the user of your model. There you go, this is the model for predicting the problem that you have given to me. So this is how the flow looks like, and this is how the flow we will be following from on. Okay, so you have some data set, you split the data set into train set and a test set. Generally you make a split of 60-80. So 80% is your 80% of the data is the training data, and 20% you are keeping it for testing purposes once the model is trained. And you first do feature selection, and there are labels corresponding to that data points, and then you train your machine learning model and evaluate your machine learning model on the test data set. And if the evaluation on the test data set achieves sufficient accuracy, you use that model for in the real world, or you deploy those models. Okay, so let's look at this example. And you need here the question is whether you should be building a classification problem or a regression problem. So consider that you are running a company and you want to develop learning algorithms to address each of these two problems, problem one and problem two. So the problem one is you have a large inventory of identical items. You want to predict how many of these items will sell over the next 3 months. You want to predict how many of these items will sell over the next 3 months. And the problem two is you'd like a software to examine individual customer accounts and for each account decide if it has been hacked or not. Okay. So whether you should how will you solve this problem? Is problem one a classification problem or a regression problem? Or problem two, is it a classification problem or a regression problem? So what do you think? What is problem one?
Problem one is classification and problem two is regression, sir.
Okay. Anyone else?
Problem two is classification because mainly the two categories are there, hacked or not.
Okay.
So that should be the classification or the second one.
Okay. And problem one?
Mm.
Problem one, you cannot say currently anything. Not enough information has been provided.
Right. Right.
Okay, so we have one person saying problem one is a classification problem, problem two is a regression problem. Another person said problem one, we can't say anything, not enough information has been provided, and problem two is definitely a classification problem. Anyone else? Mm, okay, so let's look into this. So as one of you have pointed out, problem two is a classification problem, and she correctly identified that there are only two categories that you have to make prediction on, whether it is hacked or not. So there are only two categories that you need to predict on. So hence it's a classification problem. Now let's look into this. What you have to predict in this problem? You have to predict how many items it will sell over the next 3 months. Now you can see that this is a continuous value. It can sell 0 item, it can sell 1 item, 2 item, 3 item, 4 item, 5 item, 1,000 item. I don't know, it's a very large inventory, right? It can sell even 10,000 items. So obviously there is still, it's not an infinite number, but the prediction numbers are sufficiently very large, right? So
Yes.
you can treat the problem one as a regression problem.
Okay, sir.
Make sense?
Yes.
Even though the problem one does not look like an infinite set, but it is still a very large set, you can consider this very large set as a regression problem. Okay. So this is what problem one, you can view it as regression problem, and problem two, you can view it as a classification problem. But even that person who said that the problem one is a classification problem is also partially correct. But in general, but the classification would be from 0 to, say, if the large inventory had 10,000 items in that inventory, so from 0 to 10,000 you have to predict in one of these class. So it will be a very big classification problem, it will be a very tiring one. So in general, these kind of very large set are not infinite but large set are also treated as regression problems. But it's fair to call it also classification, there is nothing wrong, but the accuracy of that model would be very low. Okay, so we will treat problem one as regression and problem two as classification. Now next question, this one: of the following example, which one would you address using unsupervised learning? Remember, the unsupervised learning algorithm does not have a label, it only finds a relationship between the data set. Now, look at these examples and tell me which example is suited for unsupervised learning. 1, 2, 3, or 4.
Can we say the third one as a unsupervised as the automatically the model is discovering the market segments on its own?
Okay. Anything else you feel that it can also be considered as unsupervised? You think only third is, or do you want to uh, only third, or anything else?
Second can also be because it might be reading the stories, and from the stories, it might be deciding on its own after the learning.
Okay. So
So
second
second,
is, please go on. Second one.
yeah, second and third one.
Okay. So what we have one answer, second and third. Anyone else? Okay. So can you give me why do you did not choose example number one or example number four?
For considering any email address as a spam, we do label the some domain names or some senders. So I think we are being bit of precise while training the model with this particular data treated that as a spam. That is what
Okay.
I'm thinking.
Okay. And why not four?
Because there is a very specific terms use a diabetes or not the diabetes.
Mm-hmm.
Um, and that requires a very specific um, observations.
Mm-hmm.
So I'm thinking there is it's a very specific term used over there. So unsupervised, the supervised is more precise for the last one.
Okay. So you are correct though. You are completely correct. So in one, you are not using using unsupervised learning here because it's a supervised learning problem. So you are given an email and its corresponding label, whether it's a spam or not. If it's a spam, it is one. If it is not a spam, it is labeled as zero. And the goal is to learn a spam filter. What will it do? It is will actually predict, given an email, whether it is a spam or not. It's a prediction problem, so it's a supervised learning problem. Similarly, in example number 4, given a data set of patient diagnosed as whether having diabetes or not, so you have given a data set of the patient, a patient information is there, and this patient, whether it has a diabetes 1 or not, or it does not have a diabetes 0. So you have a label corresponding to this patient, whether it has a diabetes or it does not have a diabetes, and then you need to predict, given a new patient, whether it has a diabetes or not. So it's also a class prediction problem. Hence, it's a supervised learning problem. And even in the supervised learning problem, it's a classification problem. You need to just simply classify whether it has a diabetes or not. Here also, it's a super prediction problem, but also a classification problem, which is whether it is a spam or not. So it's a supervised learning problem, and even in the supervised learning problem, it's a classification problem, not a regression problem. So 1 and 4 is a classification problem of supervised learning. And as she correctly pointed out, 2 and 3 are the only unsupervised learning algorithm, because here you want to draw new insight or find a relationship between the data set. Look at this. What the question is, what is the information that you are looking for? Given a set of articles, a large set of articles from the web page, you want to group them, a set of articles of the same story. So you want to group them in a political, if all these articles belongs to a political category, you want to group all the political category. So you want to draw a relationship between the data points. So you are trying to find a new relationship between the data points. Some relationship, identify some new relationship among the data points. Here too, given a database of customer data, automatically discover market segments and group customer into different market segments. So you want to group customers in the different market segments. So here also you are trying to find a relationship between the customer, and whichever customer shares the same market segment, you want to group them together. So here in both these categories, you are seeking to identify a relationship among the data set. You are not trying to predict anything in these two categories. So second and third, you're not trying to predict, you're trying to identify new relationship among the data set. But in 1 and 4, you're trying to predict something. Hence, it's a supervised learning, 1 and 4, and 2 and 3 are unsupervised learning. Does it make sense?
Yes, sir.
Okay. So I will repeat once. 1 and 4 are supervised learning because here you have to predict something. 2 and 3, here it is supervised, unsupervised learning because you want to draw some new relationship or new insight among the data points. Okay. So moving further. So in linear regression, as the term suggests, here you are going to do regression problem. You are going to solve a regression problem. So you will have some training set, its corresponding label. It will be a continuous, obviously, and there's some learning algorithm will be there, and you want to estimate some continuous value. Say, for example, estimate a price. Okay, so let's look into this. So you have this data points. So you say there is only 1D point. You have given x and the corresponding label y. Y is continuous. X is also some feature. It's also continuous. So you have this blue colored dot is the data point here. So this is one point with x some value and y some value. This is another x value, a data point x value and corresponding y value, x and y value. And these blue dots are the label, the data points. What you want to do in linear regression is to fit a line in the data among the data points that best explains the data point. That given this new data point here, what would be the best y that you can predict? Okay, so this y is simply b naught, which is the intercept, plus b1, which is the slope, times x, plus u. U is some noise. This there is some noise in the among which is making not fit on the line but slightly above this line. So some small noise. So this is what you want to fit in linear regression. It's a linear meaning that you want to fit a line, and regression because it's a continuous value prediction thing. Does this does linear regression is at least intuitively, is it clear that what you want to do? B0 and B1 is the one that you want to predict. You want to not predict. You want to find the value of B0 and B1 such that when you draw this line, it best explains these data points. You want to find B0 and B1 such that when you draw this line in the data point, it best explains these data. You can never predict because it's a random noise. So what you want to find is B0 and B1 that best explains the data. Is the intuition clear?
Yes, sir.
Okay, so you want to just find the best line that best explains the data, and you want to find this B0 and B1. You cannot find because it's a noise, and we in general don't find U there. Okay, let's look into how to find B0 and B1. Say for example, now this B0 in this is become theta because theta is the one that we use for parameters. In general, in many of the literature and in many books that you will read, they will generally use theta as a parameter. So theta is the parameter of the model that you want to find, theta naught and theta 1. So how you find theta naught and theta 1 is that you minimize this equation. So h theta x1 is the xi is the point, so this is the data point, and you fit this value theta naught plus theta 1 times this x, and it should predict value yi. It will predict some value, and you want to minimize the distance between the actual yi and the predicted yi, and the whole square of that. That will give you the error in this prediction. So this is the prediction of h naught theta x I, and this is the actual yi. This is the difference. This dotted line is the difference, and you squared this dotted line, and you want to minimize this dotted square line distance on an average sense. So if you minimize the distance between the prediction and the real value, so the best you could do is to find the mean value of it. It will pass through in between the value, and that will best explain the data point. So this is called mean squared error, where you are trying to find the mean of the squared error. So this is the error. The dotted lines that you see here is the error in the prediction, and the square of that error is the one that you are trying to minimize. Can you see that this blue dotted line will become the best prediction? Eventually, if this is if you minimize something, minimize this value, you will be actually be minimizing the error in the prediction, and that's what you want. That what is the line that best explains the data point with minimum error, right? You want to minimize the error in prediction, and that's what it is doing. It is minimizing the error in prediction. Can you see that it is minimizing the error now? That if you minimize this equation, it is actually minimizing the error in prediction, and it finds this line that best explains the data point. Can everyone see this thing? Should I repeat, or is this okay? Okay, I will repeat one more time. So h naught, theta naught, and theta 1 is the value that you want to find. But how will you find this theta naught and theta 1? You want to find this theta naught and theta 1 such that whatever this whatever the value would be, whatever the prediction that you will get from h theta x, whatever you will get the prediction from this, should be such that the actual value and the predicted value should have the minimum error, the least mistake that it can make. That's what you want, right? So this is the error term. H theta xi is the prediction, and yi is the actual value. The difference is the error. The square distance, the square of error, is what you are minimizing. So once it becomes the minimum, it reaches the minimum value. So theta naught and theta 1 would be the minimum value of this. So it will best explain the data point. So once you minimize this, you will get theta naught and theta 1 such that it is very close to the predicted value for all the data point on an average. Hence, this line best explains the data. Okay. So similarly, so this is how the entire things looks like. Now you needed to find you needed to find this beta naught and beta 1, which is actually theta naught and theta 1, and this is how you find theta naught and theta 1 by minimizing the error in prediction. So you want to minimize the error in prediction. You want to choose those theta naught and theta 1 that minimizes the error in prediction, and that's what this is doing. You want to choose that theta naught and theta 1 that minimizes the squared error in prediction, and this is one way. There are many other ways. You can just simply use absolute norm 2, not square but mod value. That's also perfect. that you are trying to minimize the error in the mod way, the actual mod. Here we are just using square, you can use mod too. But there are many other ways to minimize. But this is one way you are minimizing the error in prediction, and you want to choose that theta 1 and theta naught and theta 1 that minimizes the squared error. Okay. So once you have minimized the squared error, but there are this some noise there. Say for example, some random noise is there in the line. So what can we do? Say for example, in this plot, there is this. You know that this looks like a quadratic curve, and you want to fit a quadratic line. A straight line will not explain this thing well. Here you can see that this actually looks a straight line, so it straight line can explain this. But here you look like more look like a quadratic curve than a linear curve. So we can design a more complex linear regression model. So what we can do is, so when we have a data point, this x is a data point, it looks like a more a non-linear function. So the linear x model theta naught plus theta 1 x will only fit a line here. But if you make theta naught plus theta 1 x plus theta 2 x square, now you need to predict theta naught, theta 1 and theta 2, but it will be able to predict a non-linear function. If you increase more thetas, it will make it even more fit the model really well. It will fit the data point really well, but it will overfit the data point rather than explaining it. So this model is a better model than this model because now it is now fitting to noise in the data, not the actual data. So this is the perfect model. This is underfitting, this is perfectly fitting, and this is overfitted model. I will stop here now. I think today we had sufficiently uh, long discussion though. Tomorrow we will see all these things in. Tomorrow I will have one more section on polynomial regression, maybe 3-4 slides more, and then we will see the hands-on tutorial on linear regression. I will share this thing now, and tomorrow you can ask me more questions on if you are not able to follow linear regression. Please ask me again. I think today uh, I feel like linear regression is slightly complicated. You need to understand why is this error minimizing here. You need to find theta naught and theta 1 such that the error needs to be minimized, and that's what it is doing. We'll see more on the tutorial section that how do we do this. But yeah, I will ask you to go through the slides again and see if you have any doubt, and then please let me know. Okay, I will share the slide. Please give me a few more minutes. I will share the slides now. Can someone confirm if they can see the slides or not? Can you see the slides? I just posted it
We
on.
can see them.
Okay, I just posted it on chat. So please download the slides and uh, please look into the slides. We'll see you tomorrow on the tutorial section then. Please ask me if you're not able to follow the linear regression slides. We will spend some more time in doing linear regression and then move to tutorial. Okay, see you tomorrow then. Bye. Thank you again.